So welcome everybody. This is a video I made on section 4.4, basically for the sophomores who are not in class today. It's my expectation, sophomores, you'll watch this video and kind of take notes as if you were in class. We kind of went a little more slowly today because you weren't here, and so we had about a half hour of class to work on homework. And so you just watch this video, take some notes, you can pause it kind of as necessary. I'm going to try to cover exactly what we covered at the beginning of class today. So we talked about isosceles triangles today, and I think we know what an isosceles triangle is. An isosceles triangle is a triangle that has two congruent sides. So this is an isosceles triangle. We covered a little bit of the vocabulary related to isosceles triangles. So that the sides that are congruent are called the legs. So this triangle has two different legs that are congruent. The side that is not one of the legs, the one here down at the bottom, is called the base. The point at, in this case, the top, but in general it's the point that's between the two legs, is called the vertex. And then every angle also has a name too. So this angle right here, which is the angle whose vertex is the vertex, is called the vertex angle. And the other two angles that are down here at the bottom, so this angle and this angle, are called base angles. And such as some vocabulary related to isosceles triangles. We can name all the sides. Two of the sides are legs, one of the sides is a base, one of the angles is the vertex angle, and the other two are base angles. Now, I drew that previous isosceles triangle with a base at the bottom. That's normally how we think about isosceles triangles, but you can certainly, does not need to be the case. In this case, the base is at the top. Right? In this case, the base is kind of on the side, right? In this case, you can imagine, if these are congruent, the base is kind of right there. So just don't think that the base is always sort of on the bottom. Okay? One of the things that we're going to talk about with isosceles triangles is, let me think about this isosceles triangle. Imagine I cut that out kind of as a piece of paper, and then I kind of folded it kind of down the middle. This is the dotted, and I kind of took that and can imagine and kind of folded it a piece of paper over so that the two different sides matched. Wouldn't this angle sort of be the same as that angle if you kind of folded it over? And that's going to be one of the important ideas related to isosceles triangles, which is if a triangle is isosceles and you kind of fold it over, the base angles end up being the same. So we're going to talk about that right now. And that sure sounds like a theorem. And that's the first theorem we're going to talk about today. There's only going to be two theorems today. Relates to this idea of the base angles. So we're going to write that if, and by the way, I'm going to write this theorem two different ways, which we'll talk about in a second. If two sides of a triangle are congruent, then the angles opposite them are congruent. And what I mean by that is, think about this triangle up here. If two sides of a triangle are congruent, then if you think, where is the angle that's opposite this side? Oh, it's right over there. And where is the angle opposite that side? It's right over there. So the angle kind of opposite or across from those sides end up being congruent. Basically, it's saying the base angles of an isosceles triangle are congruent. Turns out this theorem actually has a name, and the name of the theorem is the isosceles triangle theorem. So if you want to use this in a proof, you certainly can call it the isosceles triangle theorem. My recommendation, though, is actually that you don't. Because one of the things I don't like about this particular name is that you know what word is not in this anywhere is the word isosceles anywhere. So it ends up being a little bit confusing. This is the isosceles triangle theorem, and we're going to talk about that in a second. The next thing we're going to talk about here is another theorem, because it turns out if you go back to the previous theorem said if the sides are congruent, then the angles are congruent. Well, if you think about it for a second, the converse of that is also true. So this next theorem we're going to talk about is actually the exact converse of what we just wrote. And it's literally just replacing sides with angles and angles with sides. So if two angles of a triangle are congruent, then the sides opposite them are congruent. And what I mean by that is in this triangle up here, if you have this angle is congruent to that angle, then the side opposite this angle is over here, the side opposite this one's over here, so if the angles are congruent, the sides are congruent. Well, guess what? This one also has a name. It's kind of a funny name. It's actually called the converse of the isosceles triangle theorem. Okay, you can use that name. You can call this one the converse of the isosceles triangle theorem. It's my recommendation, though, that you don't, because it's super easy to mix up which one is the isosceles triangle theorem and which one is the converse of the isosceles triangle theorem. And the names, the actual words of the theorem aren't that much shorter, right? So I'm almost never going to refer to these. I'm always going to just say if two angles of a triangle are congruent, then the sides opposite them are congruent, or I'll say if two sides of a triangle are congruent, then the angles opposite them are congruent. I just think the names actually don't really refer to what they are, because if you read the words, it's not obvious which one is the converse and which one is the real isosceles triangle theorem. The word isosceles isn't really even in those. Okay? And you end up using these kind of solving for x more than you in proofs anyways. Let's actually talk about a couple examples. So I'm going to do about 4 examples related to this idea. Here's our first example. So it's clearly an isosceles triangle. If it's an isosceles triangle, we know that the base angles end up being congruent. So we know that those angles end up being congruent. We also know a triangle has to add up to 180. So we can say 30 plus x. Well, if this is x, this has to be x up here. Plus x has to equal 180. So that ends up with 30 plus 2x is equal to 180. That gets us 2x is equal to 150. And then, of course, x is equal to 75. Okay? Most of the homework problems tonight are going to just be kind of solving for x kind of stuff like that. Let's look at another example. Okay, so here, I made a mistake actually in the diagram. So in the actual diagram, sorry about this, you would not have actually known that these were the same. You were supposed to know that these angles were the same. Sorry about that. But if you know these angles are the same, then guess what? You know the sides are the same, right? Because if two angles of a triangle are congruent, the sides opposite them are congruent. So here, the first thing you want to say is that 2x minus 4 is equal to x plus 5. You may wonder about this 2x plus 2 over here. It has nothing to do with the whole problem at all. That's actually not, if you know these base angles are congruent, you know that the sides are congruent, this actually is the base. We don't care about the 2x plus 2. This is a relatively easy equation to solve. We just subtract x. X minus 4 is equal to 5, and x is equal to 9. Okay? Well, again, most of the problems on tonight's homework are just like that. Okay, here's another one. Now, when you first look at this problem, you're probably thinking, well, wait a second, shoot, I don't know how to solve for x. This doesn't look like an isosceles triangle at all. But my general advice when you're solving problems is to see if there's something you can figure out that would actually help you with the problem. Can you actually figure out this angle right here, which is y? Well, sure you could. You know a triangle adds up to 180, so we can write 56 plus 62 plus y has to equal 180. I believe this gets us 118 plus y has to equal 180. And y has to equal 62. So this y right here, let's see if I can figure out how to use the eraser here. I think I can. Oh, I figured out how to use it. Great. Okay, so this y has to be 62 right here. And suddenly you're like, oh, that's incredibly helpful, because look, these angles end up being the same. Well, if those angles end up being the same, then we know the sides opposite them are congruent. We know this is congruent to this, which tells us that x is equal to 42. Okay? Okay, here's our last example. I want you to see how this might kind of come up in a proof. So I'll give you a second. You might want to just pause the video and kind of copy this all down. I'm going to just kind of squiggle the given here. And then my general advice, again, hopefully you've paused the video to copy that all down in your notes. My general advice is let's kind of go through the given and see what we know. So If M is the midpoint of segment JK, why would I tell you that? Oh, probably I would tell you that because you then know that JM is congruent to MK. Right, that totally follows from the first part of the given. And the reason that there would be definition of a midpoint. Okay, so now again, my general advice to mark up the diagram, we know that that is congruent to that. That's basically the second step. Then you're looking, well, there's some other part in the given. We know that angle 1 is congruent to angle 2. So if angle 1 is congruent to angle 2, why would I tell you that? Oh, that's probably because it means that it's some sort of isosceles triangle thing going on. And we can say that JG is congruent to JM. And this would be because of the idea, and I'm actually going to write the whole thing out. If two angles of a triangle are congruent, then the sides opposite are congruent. Now that also is the converse of the isosceles triangle theorem. You certainly could write converse of isosceles triangle theorem here. I'm going to write it this way because I think that actually makes it more clear. Well, look at these two steps here. Look at steps 2 and 3. Don't you have two things that both equal Jm? Yeah, sure you do. You have two things that both equal Jm. And the one thing we do all the time is if you have two things that equal the same thing, we set them equal to each other. So Jg is congruent to Mk. And that's our reason that is transitive. And we're done. Congratulations, we did it. Okay, so this is what the homework is. I want to talk a little bit about the homework. We started it in class. Like I said, we spent about a half hour doing it. Just a couple quick notes. You'll notice actually that I wrote here 23A and 24A. That means those problems have multiple parts to them. I just want you to do part A of that problem, of those two problems. You'll also notice that the homework covers 2 pages. These problems right here, problems 6, 7, and 8, are actually proofs kind of back from the previous section. They're kind of the SAS, CP, CTC proofs. I wanted to give you a little more practice with that. In the half-hour class, most of the students got somewhere entirely done with the first part and a little bit done with the second part. Hope you had a fun retreat, and thank you so much, and have a nice weekend. Bye-bye.